Okay, so we are all set. So thank you very much, Mr. Mignano, for this introduction. And I guess I've been here at the Newton Institute quite some time back, and so I'm happy sort of to be here again and see a flourishing institute. So the talk will be about the dynamics of integrable system. I mean, both classical and quantum. And since it's integrable, I mean, we are sort of automatically restricted to one dimension, but we do have many degrees of freedom. So think of an extended system, and that's what we're going to study. Now, somehow for the audience, I thought maybe I say a few words on the blackboard before actually starting sort of the real introduction, so that you just somehow see what I'm talking about. So one of the very famous integrable models is the so-called Lieb-Liniger model. So these are bosons on R. Okay. And let's say I have n of them. N is a large number, so I have positions x1 all the way up to xn in Rn. So there are no boundary conditions, it's just working on the infinite line. And then there's a Hamiltonian which sort of governs the quantum mechanical time evolution, which has a very simple structure. I mean, so it's a sum from j equal 1 up to n. I mean, there's a minus sign here, and it's 1/2 the Laplacian, so it's just a derivative squared. And then there is an interaction potential, which I take to be repulsive, so I put here a plus sign. And then there's a sum over all pairs. And then it's the delta of xi minus xj. Okay, so you might be a little bit confused about the delta function, but what this basically means that I have to look at what people call the Weil domain xn. And you see inside I just have the Laplacian, so basically you should think of having merely the Laplacian with particular boundary conditions which are sort of encoded in this potential, right? I mean, so it's really the Laplacian in the Weil domain with I'm not going into any details. I just want to tell you what the kind of things I'm interested in. Now this model is actually integrable, so it can be solved by beta ansatz. And you see where I'm working here on the infinite line. Usually you have the problem that there are these sort of somewhat complicated beta equations which come from the boundary conditions, but since there are no boundary conditions here, you know, actually the beta ansatz formula has a very beautiful and rather explicit and simple structure. And I mean, there's a paper by Tracy and Whittam where you can read about it. So I want to maybe, you know, compute the integral kernel of the unitary. So it's e to the minus I th. Okay. And you know, this is I mean, it's just like what Jeremy had. I mean, you know, it's sort of a multiple contour integral, and there will be some determinant of something which is very explicit. Okay. Now, physically, what do we want to know? I mean, we have you know, let's say n is large. I mean, experiments maybe, you know, they take n something like 5,000 or so, so what they do is, I mean, they put all these atoms in a trap. Now, so it's just an external potential. If they are sitting in this external potential, the integrability is actually destroyed. I mean, so it will be non-integrable system, and you know, they wait a while, and eventually, I mean, they're pretty sure that what you are going to see is just the thermal state of the particles in that trap. So it's e to the minus beta h, I mean, with that external potential. And at a time t equals 0, they simply turn off that potential, and so what you will see is let's say a density profile. So here is, let's say, x. So that's my physical space, and let's say initially you know, you have sort of maybe a peak like this. Okay, so here's sort of the density initially, that just comes from whatever is the precise density of these atoms in this trap. And now they've sort of release, you know, you sort of expand into the vacuum and some later time, so this is maybe time t equals 0. And at some later time you will see maybe some profile which maybe looks something like this, whatever it is. And so this is some t, I don't know, 200 in suitable units. And what you would like to predict is you know, what is the kind of profile which you see? I mean, that might be not the most exciting question, But the point is, I mean, this is one of the situations which you can realize experimentally. I mean, you know, these are real experiments. I mean, to solve these things numerically, I mean, you better forget about it. I mean, it's just too difficult. I mean, nobody can solve this equation on a computer. So anyway, so now you would think, you know, you have this nice formula, so you should be able to sort of compute what is the density at time t. And now I just have to repeat what Jeremy told us. Of course, it's a very concrete formula, but it's so dilute that, you know, sort of extracting from this formula this kind of information is sort of essentially impossible. Okay, so you have to think about something else. Now, what people thought about is, well, look, I mean, you know, it's a very simple situation. I mean, think of a gas and it's expanding. I mean, of course, you're not going to solve Newton's equation of motion. You're just, you know, many particles. It's you know, not necessarily small density. I mean, you could have sort of a fairly dense system. So what you would do is you're just going to write down the hydrodynamic equations, and then you're looking at the solution of these hydrodynamic equations, and this you can compare reasonably with the experiment. Okay? So this is why I have in this title Generalized Hydrodynamics. So let me tell you how this works here. So, the first thing what you do is what people would call conventional hydrodynamics. Well, this is just saying, look, I mean, we have three very distinguished conserved fields, which is the density, momentum, and the energy. And so I'm just going to write, you know, the hyperbolic conservation laws for these three conserved fields. And so their number is 3. Okay, and then you just solve these equations and you try to compare with what you see. But then once you have done that step, I mean, you realize that, you know, there's something completely inconsistent. After all, we know that, you know, this system has as many degrees of freedom as number of particles, so it has n conserved quantities. So if you want to write down the hydrodynamics, it doesn't really make sense just to, I mean, why would you stop at 3? I mean, you could go to conserved quantity number 4 or 5, I mean, okay? So in fact, what we will have to do is what people call, I mean, this is just explaining the title, what is generalized hydrodynamics. You have to say that the number of conserved fields is actually n, and since n eventually will be very large, I mean, we're working sort of in a situation where we have an infinite number of conserved quantities. So this makes it also mathematically a little bit more interesting, sort of something completely new. I mean, you know, of course, you know, this problem, I mean, hyperbolic conservation laws with let's say 3 or 4 conserved fields is a, you know, it's a huge mathematical enterprise and it's extremely well understood. But now suddenly we have to sort of think about the case we have an infinite number, a very, very large number of conserved quantities. Okay, so I divided somewhere I have to see my pointer. So I divided my talk into 2 parts. I mean, first I will sort of talk a little bit about this generalized hydrodynamics in order to sort of give you some feeling for that. And then the second part will be sort of much more concrete. I mean, I will try to tell you something about connected with this whole enterprise about the classical Toda chain. Okay, so here's sort of an introduction. I mean, I mean, this idea of having, you know, many conservation laws goes back, and there's one very simple model around. In fact, it looks very trivial. I mean, I have sort of just hard rods on the real line, and, you know, this is a space-time diagram. They just move like this, and whenever they have distance a, they just specularly reflect. So this velocity goes here, and the other one velocity goes here. But, you know, there's a shift. I mean, you know, this is sort of jumps by the distance a. So obviously it's an integrable system because, you know, the velocities are conserved. I mean, you know, each velocity individually is conserved. And now you can ask yourself, you know, how to write down the hydrodynamic equations for this thing. I mean, this was first done by Jerry Perkins, I mean, many years ago. I mean, he just wrote down the equation. I mean, made some arguments, but you know, nobody really paid attention. And then Dobrushin was actually sort of extremely fascinated by this problem, and there's a long series of papers, I mean, which sort of extends over several years, where he sort of studied very carefully the hydrodynamics of that system. Now, you see, you might think that this is sort of a somewhat really over-trivial system. What is surprising, what it turns out that the structure, which I'm going to explain you, is actually seems to be rather universal. I mean, whatever integrable system people are able to write down the hydrodynamic equation, it's the same structure which appears. Okay, so I will explain in more detail. Okay, and then there was sort of, you know, there's quite a gap. I mean, then Bolteghini and Sukhov, they wrote another paper where they actually also computed the Navier-Stokes convection, so there will be dissipative terms, which is a little bit surprising because, you know, you think an integrable system, you sort of think automatically, you know, it's like an ideal gas, and therefore there cannot be any dissipation. I mean, that's the wrong conception. I mean, there's a non-zero entropy reduction and all kind of other interesting stuff. Okay, so this is sort of one case which is sort of basically the only case where we have a complete mathematical control over this kind of enterprise. Now another equation which has been studied quite a bit is the KTV equation. So here that's now a PDE. So, you know, this kind of picture was first proposed by Sakharov. He also wrote down some sort of, you know, what you might call first version of generalized hydrodynamics. I mean, there's somebody called L. I mean, I don't know him personally, but he worked over many years on this problem. Now, from my perspective, I mean, the KTV is a particularly difficult case because it's a continuum equation, and once you discretize, then you lose integrability. And you know, the continuum equation, as you will see, I mean, what will play a very important role are sort of the stationary measures and you know, I mean, stationary Gibbs measures, and for this equation, I mean, to even construct these measures, I mean, it's already a highly non-trivial enterprise. And so, I mean, but people have tried. Okay, now the real start was sort of, you know, when suddenly, you know, people got really interested in this, and many people started to work on this. Is actually not so long ago. I mean, that's in 2016, and I put here sort of quite a few names. I mean, there are many more. Actually, I noticed that I left out the big shots. Okay, so there is Jean-Sébastien Gros, I mean, you know, who's sort of behind this for many years, and of course also a driving force behind this generalized hydrodynamics. And then there's also Thomas Rosen from Ljubljana, I mean, who's sort of, you know, and his co-workers who made many important contributions. Anyway, so the list is highly incomplete. Okay, now there's a recent experiment which is called generalized hydrodynamics on an atomic chip, or maybe it should be atomic chip, presumably. I mean, it seems to be better than the usual sort of optical devices, and you know, they have sort of 4,000 to 5,000 rubidium atoms, and they do exactly this kind of experiment. Okay, so they do such a thing, and they prepare this one, and they compare with conventional hydrodynamics, and they compare with generalized hydrodynamics, and you don't see any difference. Okay, it just works nicely. I mean, you know, sort of the data's fit. I mean, they do more or less what I've explained over here. But now they had an idea how one can see the difference, and sort of those who ever sort of think about hyperbolic conservation laws, I mean, you know, it's a very obvious choice to do. So rather than taking a simple hump, I mean, you bump, I mean, a hump, so you take something which sort of has two peaks, right? So they're able to do that, and then it's the same experiment. I mean, you know, they thermalize in a particular, you know, potential of this type, and they see a stationary density. They will sort of remove the potential, and then let things expand. Now the expanded picture looks. I mean, you know, I'm doing this here on the blackboard. I mean, but it doesn't look so very different than what you had before. I mean, of course it's different, but sort of qualitatively it's similar. Now you see, conventional hydrodynamics will never capture this behavior. Why? Well, because it's a hyperbolic conservation law, and if you start with such kind of initial conditions, you will develop shocks. I mean, it's just unavoidable. I mean, this is what the equation tells you. And so when you do the solutions with this initial data, you see that, you know, I mean, the idea of doing it just with three conserved fields, I mean, just fails completely. So you really have to go to the generalized, and once you do the generalized, actually the agreement is not so bad. Okay, so next thing I want to sort of give you sort of an idea of this general structure. You see, I'm just doing some talking, I mean, but I hope it might be useful. Of course, those people in the audience who ever worked on hydrodynamic limits, I mean, for them, you know, what I'm saying is sort of totally obvious, right? But maybe for the others, it's still useful to understand, you know, what somehow and one thing which I would like, you know, what you might wonder is, I mean, why 2016? I mean, why didn't they do this already 20 years ago, right? I mean, you know, all these models have been around. I mean, so what was the big step in 2016? Okay. All right. Now let's see what I do here. Okay. So here is sort of a short summary. So I mean, think of. I mean, I put here the XXC model. I mean, think of the XXC model, or you know, some other model which you like, but you know, this sort of illustrates nicely the structures. And now it's quantum But the point is that it's a lattice systems, and here you have your spins and some particular nearest neighbor interaction. Okay, so what is very important for the whole enterprise is that it should be short range. There's the Karlotchova models which have a 1 over x squared interaction, which presumably do not fall under this class. Then maybe something else is happening. But so I will emphasize the short range. Okay, so here's just nearest neighbor. Okay, and then the Hamiltonian, and as written, obviously the Hamiltonian has a density, and this Hj, that's just sort of what you see under the sum, is clearly very local observable. It just lives on two lattice sides. All right. Okay, so now we have the conserved fields, and of course what you usually focus on is their conservation law, the fact that they commute with the Hamiltonian. That's of course clear, but when you look at any concrete model, like this one, or also later on when I tell you about the Toda chain, you will find that these conserved fields also have this structure, in the sense that if I look at the nth conserved field, it will be a sum over densities, and these densities are strictly local. Okay, so the first step in the enterprise is that you have to make a complete list of the conserved fields. Now, what means complete? That's a good question for mathematicians. Okay, now I just want to, I cannot elucidate this question very much. I just want to tell you one interesting example, which is exactly this HXXC. The conserved quantities were found back in the 70s, and then written books, and everybody believed that they had the complete list. Everybody believed. Okay, so 2011, Thomas Brosen sort of computed a steady state problem, where he takes the chain and he pumps up on the right, and then he pumps on up the spin on the right and down on the left, and then he just waits for the steady state. And somehow he was able, by some magic, to actually get formulas for this steady state, through some sort of sophisticated matrix product ansatz, and he could even sort of extract physical information out of these formulas. And you look at the result, and you look again at the result, and then you realize that with the given supposedly complete list of conserved fields, you will never explain what you see. So he conjectured immediately we must have forgotten about some conserved quantities. And indeed, there are further conserved quantities which only have been known then for whatever 7 years, right? So this issue of completeness is a somewhat non-trivial issue. Okay. Anyway, so the idea is that somehow we have a complete list. Now, once we have the complete list, then of course I can compute what is the time change of the density, which since we do quantum would be this particular commutator. There is J missing here. This should be J, right? Okay. And of course, because it's conserved, whatever, there's a certain sort of current go into the side and another current going out, or if you want, so if I look, at this conserved quantity in a little interval, then it can change only through the boundaries. And therefore, this must be of difference form, and then there's by definition, is a difference of two currents. And again, these currents are, if I know that these things are strictly local, then of course the currents, because of this commutator, also have to be strictly local. Okay, so we have two ingredients. One of them are the conserved quantities, and the second thing are their currents. Well, so the next thing is to think about what kind of states do we want to allow initially. And well, you see, usually you go back to fluids, then of course, you can vary the temperature, you can vary the mean velocity, you can vary the density, and so here you have more conserved quantities, therefore you can vary more, and therefore it's rather natural to write down this somewhat formal Gibbs state, which is somewhere n equal 1 up to infinity, and then there are particular chemical potential which just tell you, how much this particular conserved quantity is conserved and thing. This should be no surprise to you, right? This is sort of the most natural way to write it down, okay? And so now you have an average with respect to this. So people in this community call this generalized Gibbs ensemble. That's a little bit a misnomer, because mathematical physics, of course, people were, since Royal or whatever, back Sinai, people were always thinking about this generalized Gibbs state. Anyway, it's a nice terminology, because once you talk about generalized Gibbs state, you know what you mean, and it's also a nice terminology because you want to distinguish between the thermal state. Right? The thermal state is really the usual one, where you just take the beta and the density, right? So I have a terminology. Anyway, so here you have this. Now, of course, these states will not change under the dynamics by construction, because they are conserved here. And so now, if you want to, like in this particular case, if you want to sort of describe something which has initial variation, I mean, you know, a priori there's no small parameter. I mean, you know, these mu n's are whatever they are, but they're certainly not small. So the only thing which is small is actually that you assume what people would call a local GGE, namely that these parameters in your initial state actually vary slowly. I mean, so I put here the epsilon just indicating that, you know, I made now this chemical potential spatial dependent, and I put a small epsilon to make sure that, you know, this is sort of not just oscillating very quickly, but sort of slowly varying on your lattice. Okay, so we have this low variation. So that's sort of the parameter which controls you know, sort of the validity of hydrodynamics. So hydrodynamics is, you know, is sort of, if you want to sort of governs the time evolution of about a special class of states. I mean, you can of course think of crazy states which are not exactly of that form, but you know, physically, I mean, this is a very good class, and certainly, you know, these kind of atomic experiments, you know, are very well covered by such kind of a formula. Okay, so now we have this local GGE, and well, now I can take my microscopic conservation law. I can average this over the local GGE. I mean, you know, I could average over any state because it's an operator identity. It will be always true, right? I mean, so this one there's no approximation whatsoever. I don't even have to assume that it's local GGE. Anything will be okay. But now I do local GGE, and now the claim, and that's sort of the big claim. Now the claim is that when I do a local GGE, and now I take my true time evolution as sort of the system moves, it will sort of produce some very complicated state, which of course nobody really knows. But at least sort of, you know, for the kind of observables which you look at, it seems to be a good approximation that at some later time I will actually see approximately again a local GGE. Now, if this really would be true, then this means that this average is shifted from, you know, averaging this very complicated quantity to modifying the local chemical potential. So now in every space-time patch I have sort of a chemical potential which is evolving. I mean, that's just sort of the label of my GGE, and the claim is that you know, I can push the average from here to here. Okay. Now that's of course a big step. Now for the hard rod system, this is exactly what Dobrushin and company prove, and then for other systems maybe that's a difficult thing to do. But what I want to point out is that, you know, I mean, just simply assume this, and then you can sort of try to start this program, and you know, you now you can sort of write down your generalized hydrodynamic equations. You can try to solve them. You can sort of try to compare. Anyway, so you see, now you have a closed equation for this sort of yet undetermined sort of updated chemical potentials. Now, you know, maybe that's not the most convenient way to write down the equation, but the emphasis is here that it's a closed equation for this time evolving state. So basically, what you're saying is that, you know, if there's very slow variation, I never really leave, you know, the manifold of local equilibrium, local GGE states. And the way how these local GGE states evolve just follows from the conservation law. Okay, so now let's think for 1 second. So let's assume that now you're really serious and you want to know. Okay, so for instance, you want to study this thing. So I have the given Hamiltonian, and now the question is, what do I have to know about this Hamiltonian, right? Well, okay, so this is sort of pretty clear. You see, you know, we have translation invariance. So you know, I have here the J, but you know, this is a translation invariant state. You know, it changes to x and t, but it changes only through the parameter. The state itself, of course, is an infinite volume Gibbs state, and so I can just put here the 0, and similarly for the current. So now what you have to do is, you know, in this GGE, which has this infinite number of parameters, you have to compute the average value of the nth conserved field, and also the average current. If you're able to do this, then you can write down your hydrodynamic equation, and you're happy, and you can go ahead. Okay. Of course, you made a big assumption, but you know, this is sort of a secondary issue which I will not address in this talk at all, and which presumably is not, you know, to go from here to here is presumably nothing very simple, and you know, requires more work. Okay. So I just want to point out that the usual variables, what people do is that you know, they denote, I mean, this particular, I mean, the average of the, I mean, so this vector of conserved fields, I mean, they sort of denote by U, and then sort of by the usual thermodynamics. I mean, you can go between the chemical potentials and the sort of the intensive observable, the extensive observables. I mean, this U's by convexity of the free energy, you can basically go back and forth, and usually it's these average values for which you would write down your hydrodynamic equations, and so the coupled set of conservation laws looks formally like this. So there is this infinite vector U, and you have an infinite carbon vector, and of course they depend on all the average fields. So this is sort of the standard form. Now, one word about labeling. You see, I mean, once I have infinitely many, maybe the label n, I mean, the way how they appear in the model, maybe might be not the most convenient one. I mean, so maybe eventually you want to do some other label, but conceptually this is the thing. Now, the difficulty is the following. So if a model is integrable and not necessarily, but as a rule of thumb, you can compute the free energy, and then taking the derivative of the free energy, you can compute these average values. So just think that this is sort of the easy part. But nobody, even today, I mean, I just want to emphasize this very much. Nobody knows how to compute the average carbons. Nobody. Okay, except for the hard-rod model, which we know anyhow, right? Okay. So now, what happened in 2016 is that at some point, somehow people realized how to make what in the next slide I will call sort of an educated guess. I mean, so there's a very good guess, and presumably it's correct, but this is sort of what this whole physics enterprise started by having by making this guess and sort of realizing that sort of checking this for particular cases and then becoming more confident, and then actually trying to sort of apply this to models, which by itself is sort of a highly non-trivial thing to do. I mean, so this is difficult and a lot of work, but now we have quite a bit of results, and so presumably it's correct. So let me tell you sort of a little bit about this hard-rod system, but with the view emphasizing what the general structure is. Okay. So of course, in this case, I mean, you can do other things, but I just want to do it in such a way that you understand what the general structure is. Okay, so here I go. I mean, so the conserved fields. I mean, of course, there's a space-time label, and the conserved fields are simply labeled by the velocity, which in this case is a continuum parameter. I mean, this is sort of exchangeable here. Okay, and then of course you also have the density. All right, and then the average densities I integrate over all v, and the average velocities I normalize. I integrate over v. And in these formulas, I always leave out the xt. I mean, everything depends on xt. Okay. Now here's your hydrodynamic equation. So that's the time evolution of this function. Is sort of the derivative of the carbon. But now you write the carbon as the function itself times something which you call the effective velocity, or which depends itself on v. I left this out. So this object I call k of v. And now I want to compute what is k of v. And now I argue in the following way. I say, so let's imagine that we want to, so here is sort of one particular particle with velocity v, sort of moving like this. And of course it has a bare velocity which is v. But there's a background which is given by some given distribution function. I mean, imagine some stationary Gibbs measure which is characterized by by some particular velocity distribution f of w here. Okay, so that's the background. And now you see that, of course, this particle will be hit all the time by neighboring particles. So we'll jump to the right, we'll jump to the left. So we'll do sort of like a random walk. And of course, the effective velocity will be not the bare velocity, but will be modified by the collision with all the other particles. Okay. So I say, well, okay, I want to compute this effective velocity, so it's just the bare velocity. But now there will be sort of a correction term, and the correction term is written sort of like a collision rate. Namely, this is sort of more or less sort of, this whole thing together is sort of the number of collision per unit time which this tracer particle sort of yields. And now what is the effect of the collision? Well, it's just a shift by a, okay? And therefore you get this simple integral equation for the yet unknown kappa, the effective velocity. Now you stare at this. Of course, it's a linear equation, and this is a one-dimensional projection, so you can easily solve what the solution is. And here I've just written down for you the solution. Okay, I come to the comment in a second. I mean, so now you see here sort of one of these sort of infinite dimensional generalized hydrodynamics, and of course there's a nonlinearity of this particular form. Of course, the rho depends on f through this formula, the u depends on f through this formula, but it has exactly that structure. Okay, So this is, as proved, the correct sort of hydrodynamic equation for the system of hard rods. Now, the big discovery is that when you look at more complicated things, it will look sort of more or less the same. I mean, you know, it's sort of, so think of, for instance, think of two solitons. I mean, you know, they're moving ahead and then they make a collision, and from far away it just will look like this. The only difference is that you know, this is what people call the phase shift because they think in Fourier space. But what it really means, that maybe I should make this drawing, is that so this x and this is t here. So assume that I have sort of like an incoming collision of two objects. I mean, let's say two solitons, okay? Then there will be some complicated, so maybe I give this a different velocity like this, okay? So this is a v and that's my w, okay? So there will be some complicated interaction, you know, solution, and eventually it will separate. But what you're going to see is that, you know, after a while, I mean, of course, you know, this will be extended sort of all the way here. So, you know, you will see something still with w, and you will see still something else with v. But that's of course not correct. I mean, what is correct is you will see the w, but this path has to be shifted by a certain amount. That depends on the particular interaction. Also, this path has to be shifted by a certain amount. So the true thing which you're going to see is something like this, and maybe something like this. Okay. So this is what's called the phase shift, and so this means that what happens in this integral equation is that the a, which was just a number and therefore it's so easy, is now replaced by a function which depends on the incoming velocities, and of course it's a function which you have to compute on the basis of the model which you are actually looking at. And now you have sort of the structure which is supposedly quite universal, namely that you know, there is this conservation law, and then there's a linear integral equation which determines what is the effective velocity, and therefore gives you sort of a closed equation like over here. Okay, and the claim is that now, if you do quantum mechanics, I mean, you know, then the issue of statistics is a little bit more complicated. But for our purpose at the moment, I think it's good enough. The claim is that whatever model you look at, I mean, you will find that particular structure. Now, of course, it's a guess because you see, I mean, you know, I mean, at no point you actually you compute the average current. I mean, you sort of make an ansatz of what the average current would be, right? I mean, so maybe, okay. But people check, and people are very, very confident. Okay, so now I want to come to the Toda, and so now sort of was challenged, been thinking about the Toda, and so I asked, you know, I mean, so what about doing this program for the Toda, right? Now, the reason why you want to do Toda is, first, it's sort of nice discrete. I mean, so all the quantities which you want to look at are sort of well defined in a way, and you know, the question of existence of solution, all these things sort of you can do. But the other thing, which I mean personally, you know, my personal motivation to do Toda is that you know, Toda is a classical system which you can certainly, you know, do large simulations. I mean, 4,000-8,000 particles is no difficulty, and my hope is that if you could figure out what are the hydrodynamic equations for the Toda, which I don't know yet, at least I'm not sufficiently sure, then we actually could compare it with fairly sophisticated numerics, and we could sort of do a much more precise check of the validity of hydrodynamics. I mean, much better than you could ever do in any quantum mechanical model. So that's my personal motivation. Okay, so let's have a look at the Toda. So here is my Hamiltonian. So you have this exponential interaction. It's written in terms of the stretch already, which is of the positional difference. Now, just one word always produces confusion, but it's a good occasion to say this. You see P and Q, and now you think of particles sitting on the line. That's the wrong picture. I mean, just forget about it completely. What you should think about this equation, it's a discretized wave equation. And so J is sort of basically my discretization parameter. And so when I talk about continuum, it's that parameter which goes through the continuum. It's just like a standard field theory. You have a lattice, and at each latticite you happen to have a P and a I. It's like a nonlinear Schrödinger equation. If you discretize the nonlinear Schrödinger equation, you know, you have a wave function sitting at each lattice point, and you should think in these coordinates. And that's sort of, the whole thing will go in these coordinates. Okay, anyway, so here you have this thing. And now what you know, and Flaschka realized that if you introduce these extra variables, you can sort of write down the equations of motion in a different way, and you can sort of very easily sort of obtain the conservation laws. I mean, they did this more or less at the same time. I mean, Henault first obtained, all the conservation laws, and then he looked at his formulas and he realized that the conservation laws which he had written down were actually highly non-local. And of course he was worried. I mean, this somehow doesn't seem to be the case. And then at the very end of the paper he says, I can do a transformation to make them local. And then of course, right after that was the paper of Flaschka, so somehow they must have communicated. I don't know the story, but in any case, I mean, so here's what they found. So you introduce sort of a Lax matrix, which is this tridiagonal matrix. Okay, so A and J, B are defined over here. And so I'm now on the torus, well, I'm in latticide with periodic boundary conditions. And then there's also another matrix which is called Bn, because I'm on n laticides, which is anti-symmetric and which is given by this particular expression. And the evolution equation sort of transforms into this simple identity, and of course if you take sort of infinite volume limit, I mean then you will get two-sided Jacobi matrices. I mean we'll go all the way to plus infinity and minus infinity. Okay. Now what is for our purpose? What is sort of what is the use of the Lax matrix? Well, I mean there is a very simple formula for the conserved quantity. So if you want to know the nth conserved quantity, all what you have to do is you have to take the nth power of the Lax matrix and takes its trace. Trace, I mean that's wonderful. Why? Because it's a sum over all J, and so this means that I see already immediately what is the energy density, which is not always so completely simple. Anyway, so here, for instance, if I do this for the Lieb-Linear, nobody knows how to write densities, but here the densities are very simple. I just have to take the JJ matrix elements of Ln. All right. Now it's this quantity which obviously has a limit, because when I take n to go infinity, because I have the JJ, I mean, okay. Now you see it's a tridiagonal matrix, and so L to the n, I mean, think of this as a sum, and the terms in this sum, I mean, will just never go very far away from the two endpoints J, right? And so you see that I mean, this is maybe an overestimate, but in any case, I mean, these things are obviously local. I mean, they only depend on variables between latticide J minus, presumably should be almost n over 2 anyway, between J minus n and J plus n, okay? So the densities of the conserved quantities are definitely local, and as I increase n, of course, they become sort of more and more delocalized, right? Okay, so that's good. Now let's look at the carbons. So I looked in the literature, and to my big surprise, nobody ever computed the carbon. There's a very nice book by Toda, but no, he doesn't give the carbon. So here are the carbon. No, wait a second. What did I want to do? Okay, yes. Okay, so what's happening here? Okay, so here comes the carbons. I mean, so since you have such an explicit form, you can work out the carbons, and they again have a rather simple structure. Here I look at the carbon density, and it's written as L to the power n as before, but then it's sort of what I call L of. L of is just sort of the Lax matrix, and I deleted the diagonal. It's just the off-diagonal part of the Lax matrix. Okay, so you see that the carbons, I mean, clearly, they're not conserved. I mean, otherwise I would have to write them as some power of L to the n, but there's this funny L of there. Okay. Now, do we have all conservation laws? Answer is no. Why? Well, you see, if you think physically about such a system, have this exponential potential, I mean, if I just let it go, I mean, it will just sort of evaporate forever, right? I mean, it will not, there's no confining mechanism. So for a real chain, I mean, you put them somewhere at the ends, and then you can pull or you can press, and so there must be a pressure. The pressure is sort of like a boundary condition. Now, if you use equivalence of ensembles, I mean, there's a book by Cedric and Stefano Ola, I mean, who sort of investigate these equivalence ensembles in great detail. What you find is that what you have to do in order to to include this internal forcing is something very simple. Namely, what you have to do is you have to the stretch is actually conserved. You see the stretch. Maybe I should go back. You see the stretch is already written as a difference. And so you can see that the stretch is, it's up here. It's a difference, and therefore the time derivative is already a difference, which is nothing else but the velocity, right? And so it clearly is of difference form. So the stretch is conserved, and the dual is then simply, the exponential of that. And when you sort of think about this, you realize that this parameter, which I call P here, is nothing else physically but the pressure. So you see that the potential which the stretch sees is actually the exponential to the left, and then there's a linear potential which goes to the right, which comes from this thing. And of course the pressure, in order to have a stable system, must be positive. Okay. Okay, so now we have everything done. Now let's look at the GGE partition function. I mean, so you know, I have the dq dp. I have this stretch parameter here. I mean, you know, I could have written this. Maybe I should actually have. I mean, you know, it's a linear sort of volume preserving transformation. So think of the Q as a R already. Okay, so I have P is sort of on the whole real line, and the R as written is still on the whole real line, and okay, and then I have this GGE, which is sort of, you know, the sum from n equal 1 up to n with particular chemical potentials. Now here I have sort of the nth power of the Lax matrix. Well, you know, I mean, this must be some sort of power series, and why are we not a little bit more ambitious and just put some general function here? Now, I don't know exactly what class of functions I can put. I mean, you will see later on, I just haven't worked it out. I mean, but you know, this is something which can be answered. But for instance, you know, I can take you know, just finite power series. It will be certainly okay, as long as I keep the even terms, the highest even terms, sort of, you know, stabilizing these things. So it's like the usual potentials. I mean, you want to have something which is going up to have a finite integral. Okay. All right. So now we have this thing, and now you see the free energy of this object would be. So I give you some nice function, and then you want to take the logarithm. Okay. Okay. So the question, this would be this. So this depends on the potential V. I mean, you know, this V here, and it depends on the pressure, and I have to take this limit. Okay, so this looks not so easy, right? I mean, how would you do it, right? I mean, okay, so let's look at it a little bit more carefully. Let's see. I'm not sure what I did as the next thing. Okay, I give you the result. Okay, all right. Okay, so here's the result. I mean, so the claim is that when I look at this free energy, can be written in terms of a variational form. Which to some of you might look familiar. So anyway, so first of all, there's this some funny operation with, you know, differentiating with respect to the pressure. So I will forget about this for a second, but the real need is, so to speak, what I call this mean field free energy, which is given by this very particular variational formula. Then we have to minimize overall rho. I mean, rho is normalized to 1, and well, so here's sort of the potential term. And here you see an entropy term, and here you see an interaction term, which is actually logarithmic, which somehow tells you that somewhere in the back there must be sort of, you know, the log gas in one dimension. Okay. Okay. Now, if we want to, so if I call the so the minimizer is unique. I mean, you see, this is linear, this is convex, and you look at, so this is not the principal part. This is the pressure. And you look at this thing, you also find that it's sort of just convex up, right? I mean, so this is a nice convex function, so there's a unique minimizer. And if I do this funny operation, then you see that if I want to compute now the expected value of the nth conserved quantity, this is up to this differentiation, it's integrating over the minimizer. It's the nth moment of the minimizer. So you see that the minimizer is actually sort of like a spectral measure. It's what people call the density of states of this Lax matrix. And now I can give you, I explain you where this comes from, but I want to give you first what is now the picture of our dynamics. So imagine that I take this Toda chain, which sort of, I don't know, reasonably large, and I put something initially which is not too crazy, okay? And now I take a little stretch, maybe 500. I look at that stretch, and I look at the Lax matrix in that stretch. Okay. Now this Lax matrix is a random matrix because, you know, I have random initial condition, but it will have a reasonably well-defined density of states. I mean, that's exactly this rho min. You see, I mean, and of course this rho min will depend on time. It will depend on space. But if I look at a little volume, I mean, we'll have a definite rho min. And so the claim is that, you know, there's lots of motion going on, but the rho min, because, you know, the eigenvalues of the Lax matrix are actually conserved, the rho min will be a slowly varying quantity, and that has a good chance to be sort of governed by a closed equation. Yes?
It looks like your V's have to have very special structure, and that doesn't seem to have been something physically you would have wanted to start with.
Why do you say V has a very
It
special?
should be a proper potential, but originally, why?
Well, I mean, you see, before I was just looking at the power series, and in order for the integral to make sense, I realized that, I must, the largest must be even and must have a positive prefactor, right? I mean, this is, it's just when you write down a Gaussian integral, I mean, it's the same thing, right? I mean, you put a perturbation of, you do 5-4 theory. I mean, the first thing what you say, we have. It's something similar. I think this somehow has to, if there would be a more complete theory, I understand what you're saying, right? But I think in some more complete theory, maybe one could answer. Okay. All right. Now I just want to mention sort of somewhat surprising coincidence is that in case you have the quadratic case, which is obviously the simplest you could imagine. So I mean this potential is quadratic, and so let me go back. You see here you will simply have. You have simply the trace of L squared, right? I mean, which of course is sort of the simplest function you can imagine. Then with totally different motivation, I mean, Alain Bouchot and Alice Gouinet, and sort of some time back, they actually found the exact solution of this variation principle. And here's a formula, their formula for the minimizer. So you see, you have a Gaussian, and you have some other particular thing which is not too complicated. I mean, it's this very particular integral. But the thing which I wanted to point out is what you can see from this formula is that when you let p go to 0, then this interaction term disappears, and then of course you get just merely the Gaussian because it's a Gaussian potential. But as you crank up p, then this one will become more and more important. And in the limit as p goes to 0, you see that it will go over to the Wigner semicircle law. Okay. Now, of course, if this is not quadratic, I mean, there's no reason why we should find an exact solution. But it's nice to have at least one non-trivial example, okay? Okay, now let me tell you how you can do that, okay? Okay, so the first idea is that you sort of peel off a little bit of your potential, and then I sort of peel off the quadratic piece, okay? So here's what I did, okay? And that's sort of simply the rest, okay? And now you wonder what is Ln under this Gaussian measure? I mean, quote Gaussian. Of course, it's a highly non-Gaussian measure, but it's Gaussian because sort of it's quadratic in L. Okay, so what is Ln under? Okay, so that's a simple computation, right? I mean, you can write down Ln squared more explicitly, and okay, so you do this simple computation, and what you find is that the diagonal happens to be normal distributed independent. Okay, so here I put the distribution just to make sure. And the off-diagonal elements are distributed according what people call the chi distribution, with a parameter which is 2p minus 1. And you see, I mean, this of course is positive because the a variables in the Lux matrix are the exponential of something, so they are positive variables anyhow. So this is a distribution on the positive line, and they are also IID. Okay, so now it looks very easy. I mean, you just go to the books and you find the density of states and realize, I mean, it's not in the books. I mean, computing the density of states for such kind of random matrices is sort of somewhat difficult business. And so okay, so you might, you just cannot find it. Now, there's one thing which I want to point out. I mean, there's this sort of strange factor 1 over square root of 2. I mean, you might say, you put some other factor that will work easily. I mean, what I'm going to tell you works only for the 1 over square root of 2. Okay. Now, now there is a beautiful result by Dumitrio and Edelman who tell you that not exactly this thing, but there's something similar on which they actually are able to compute the density of states. And there it's also a triangle matrix, and it's a so-called, I mean, it's a Jacobi matrix associated to the beta ensemble. So you will see in a second what this means. I mean, so now the diagonal is just exactly like this one. But the off diagonal has also the 1 over square root of 2, but it's not IID, it's only ID. I mean, in the sense that these are independent random variables, but you see that the parameter which is sitting in this chi distribution is now linearly changing with my index. So what I call a linear ramp. It's just linearly changing. Okay? But now for this matrix, they tell you that they can actually compute what is the distribution of eigenvalues, and therefore also the density of states, but they have an explicit formula for the distribution of the eigenvalues, and it's given by what people call the beta ensemble, which there are these famous values beta 1, 2, 4, but here it's for general beta. I mean, beta is at that stage, just anything. It's just this parameter here, and it has sort of the usual structure. You have sort of the Gaussian part here, and then you have this power of the van der Monte determinant. So now what are we going to do next? You see, the trouble is that it's similar to the L matrix, but it's not the same. But now comes sort of the very simple observation. Beta is something which I can take, is still a free parameter. I can do whatever I want with it. So why don't I take beta equal 2p over n? I mean, that's permitted, right? So n will be larger. Actually, beta will be very, very small in the limit. Okay, so now I put the p over n. Now you see this is a very nice thing. It's just a linear ramp, but the slope is 1 over n. So whenever I compute free energies, I mean, I can just add up. I mean, it's a slowly varying function. All right, so why don't we do that? And now let's see what we get. Okay. Well, so now you see what we have to do is. So here's this assertion about the linear ramp. I mean, so I have to compute this thing, and the claim is that it will be just sort of the Lax matrix. I mean, the quantity which I want to compute, but then I have to do this linear ramping. But it's just a p parameter which was sitting in the chi distribution. Therefore, it's just up. Okay, so this is an identity. Now the point is that this object, this is a very nice mean field problem. I mean, here I've written down again the partition function just to make sure that you remember. So I have to integrate over lambda 1 up to lambda n. Now there's the v tilde, but in the measure there's the x squared. So when you combine everything, you get our original potential, and you get this mean field interaction. That's sort of beautiful. Why it's beautiful? Because if you know anything about statistical mechanics, you know how to do such problems. It's a straightforward mean field problem. You see, straightforward mean field means that I have a pair interaction, which is this logarithm, but then there's a 1 over n sitting here. So if you do this, you get this variational form. Okay. So let me spend sort of still. There's not more I can report on, sort of positively report on the Toda. I would like to compute the average currents, but this, of course, I don't know. Okay, so So let me say a few words for your entertainment, sort of connection to Dyson's Brownian motion, which is sort of pretty obvious, but I think might be still sort of nice to see. You see, first I thought that I couldn't find in the literature. Of course, people have there's huge literature on these kind of mean field limits, but then when it comes to the specific singularity of the logarithm, then even the latest reviews they say okay, barely the logarithm, but they just cannot do the logarithm, things like this. And then I finally discovered a very nice paper by Israelson. I mean, he does it sort of exactly in the right way how to do it. And of course, this paper relies on having just simply exactly the logarithm and nothing else, right? I mean, the other things are more general methods, the logarithm and then okay. They always wanted to look at general function. I'm just looking here at the logarithm, and you see that these techniques sort of work very well. So let me just sort of flash a little bit, so you get some idea of what the structure is behind. So here is this mean field Dyson Brownian motion. So here's the external force. I mean, you have this is sort of P is the strength of the mean field interaction. You have independent Brownian motion, and you want to compute the empirical measure. And then of course there's an evolution equation for this empirical measure. So you assume that at the initial time there will be some limit, and then you get this evolution equation, which is sort of pretty obvious. I mean, this is just sort of, this one would be just the non-interacting evolution, and then you will get this particular mean field term, which is just of the obvious average of this thing, right? And now you can look at the stationary measures. So these are the ones which I had before. I mean, when n goes to infinity, locally it will look like a product, which is given by the unique minimizer. You can what else do I want to say? Let's see. Yeah. Okay. I mean, okay. So you can also. I mean, when you prove this results, I mean, part of it is actually proving that you have a. So this sort of uses definetti. I mean, or Hewitt Savage. I mean, basically, you use sort of the fact that because of this mean field interaction, sort of your measure is permutation invariant, and then you first prove that the limit will be determined by the minimizer of a free energy function. The free energy function is the one which I've written down for you, and it has a unique minimizer, therefore it must be a product. So this is sort of what happens here. I didn't write out this down, but you can I mean, from this you can sort of figure out the stationarity condition is putting this equal to 0, and then you look at this thing and you discover that it's just identical to the Euler-Lagrange equation of your free energy function. So all these things fit together. You can also worry about fluctuations, which for some other reasons actually are of some interest to me. And so you see, when you do the log S, of course you will not have it will be not Gaussian, it will be log correlated, it will be not a Gaussian. But here it's sort of a very weak, and in the very weak thing it just sort of goes in the usual way. I mean your fluctuations are of order 1 over square root of n. I guess there's a bracket missing here, and then so if you let's say in the stationary case you subtract the mean and then you do this sum. Then you find that the limit will be sort of an infinite dimensional Einstein-Uhlenbeck process, which people who have seen these things, is a totally familiar structure. I mean, so here comes sort of the noise strength, sort of, it depends on the density of states, and otherwise it's a usual structure. The only reason why I wanted to point out to you is that when I first looked at this, I was always worried about having this in Dyson's boundary motion, having this 1 over x singularity. But when you write it in weak form, actually, it sort of comes out very nicely, and then sort of exactly the way how it should be. I mean, as you write down it in weak form, so this is just some test function, you see that this term actually appears. I mean, here's sort of the linearized one, but it's this term. And so you see that so you always have to assume that f is sort of sort of at least sort of differentiable, because otherwise, the limit would not make any sense. But if it's differentiable, then you see by this combination, I mean, this x minus y singularity sort of is always exactly balanced, right? I mean, so this is how it comes out. Okay, so I think my time is essentially up, and so let me just sort of repeat what I was trying to say. I mean, so what would be very important would be to have a direct computation of the GGE average carbons. We're working on checking the predictions through sort of linearized dynamics, and of course, the long goal would be to have a comparison with quantum dynamics. Thank you very much.
Is there any question? Yeah.
So, for instance, if you add a small perturbation to your XXZ, for instance, an interaction with the next to nearest neighbor, so first the integrability structure is lost. So, do you expect that, for instance, remains some trace of this behavior for intermediate times? Because so you expect, I guess, not the generalized Gibbs sum, but just the Gibbs sum, and you get hydrodynamic, not generalized hydrodynamic. Maybe there is some, I don't know, what you expect.
Yeah, we had so a year ago we had actually a conference at the Simon Center, which was focused exactly on that issue, right? And Fabian Essel is one of the persons who sort of has been working on this, and others also. Now, the details are presumably rather complicated, but the general pictures I can very easily explain in an answer, right? I mean, so the idea is when you add now a small nonlinearity, it really looks like kinetic theory. You see, in kinetic theory, of course, your Euler, what I call the Euler equations, are completely trivial, right? Because it's just ideal gas, right? But then you have the small perturbation, which means that particles also collide, and this you try to put into the collision term, but which is still saying that at any moment you have a GGE. You see, I mean, if you look at the Boltzmann equation and if you look at the structure in the Boltzmann equation, it's saying, okay, you have a GGE, but then there's a collision term which tells you how the f function is actually changing. And so exactly the same strategy they're trying to do. So you want to build on top of now a nonlinear sort of ballistic scale. You want to add sort of this collision, which presumably end up with some sort of collision term, right? Now details are you you have to ask sort of the experts. But this is the basic idea.
That's a related question. Instead, how would you can you distinguish between which is the quantity which distinguish between a solvable interacting with respect to a non-solvable? Because if you cut the delta there, it's still solvable, but it's non-interacting, right?
Okay.
So
No, I mean, so at least on that level, I mean, so the way how so this is the question. You know, there. I mean, if you think about integrable models, there are so-called non-interacting integrable models like ideal gases, and ones like the Lieb-Linear, which are interacting, obviously, right? I mean, but they're still integrable. So no, I mean, I think it enters in a very simple way. I mean, once you know the hydrodynamics will simply decouple when I look at the non-interacting integrable system. Will decouple. You know, you will the nonlinearity will just go away. You see, you can see this in this thing here. So look at this equation. You see, A is the interaction. So you know now that you let A go to 0, and then you just find V f of V. So they just decouple, and I think that's what happens when any free fermion model will be of the same type.
So for instance, if you do this in the Lattinger model, which is apparently interacting but is mappable in 3 bosons, you guess there is not a term.
Yeah, I don't know. I don't know about Latin. So yeah.
There is another small question. Yeah, so maybe we go on with the next speaker. Thank you again.